At this very moment, while you're tuning in, an extraordinary event is unfolding across our solar system. Since the detection of 3 Atlas back in July, the situation up in the heavens has steadily grown more bizarre. This age-old traveler from beyond our stars has puzzled experts right from its initial sighting. Yet, its bizarre composition and eerie emerald luminescence no longer stand as the most perplexing features. Far more intriguing now is the trail of phenomena trailing behind it. What was once a reliable and orderly expanse of space has morphed into a bustling thoroughfare, crowded with objects drawing together in formations that challenge all odds. Be it a cluster of 7 comets showing up in unison or a new surge of asteroids streaking by our planet, the spectacles lighting up the evening heavens are profoundly unusual. Consequently, stargazers find themselves compelled to ponder, what exactly is 3 Atlas inflicting upon our solar domain? Join me for this midnight delve as we probe if this represents the cosmos's most staggering fluke or a development of deeper significance. Part 1. A surge of asteroids approaches. Mid-September 2025 ought to have passed uneventfully, merely a standard stretch of everyday celestial movement that observers log with exacting detail prior to shifting to fresh scans. The cosmos, however, plotted a divergent course. During those sharp fall days, an altogether novel spectacle emerged, a grand procession among the stars that sent researchers rushing to their instruments and everyday folks questioning whether this surpassed simple chance. The lead act appeared ahead of the rest. Asteroid 2025 FA22, a colossal slab of stone the size of a peak, spanning from 130 to 290 millimeters in diameter. On September 18th, it glided by Earth scarcely more than twice the Moon's distance, about 835,000 kilometers distant, near sufficient to grab attention in the news, distant enough to ensure peaceful rest. Yet this is where the tale takes a captivating turn. FA22 traveled with company. Far from the usual solitary drifter on its routine path, rather, it resembled the debut performance in a stellar arena where various actors stepped forward one after another in quick order. The diminutive near-Earth body 2025 RJ2 had preceded it by 3 days, on September 15th, zipping by at only 0. 78 lunar distances, a scant 300,000 kilometers from home. To those versed in the skies, that's akin to a friendly clasp. Still, these events stood apart from random occurrences. Over the course of that very week, scores more intruders at sub-lunar ranges traced their paths through our immediate cosmic vicinity. Every bit documented and monitored via the worldwide array of orbital watch networks. Quantitatively, it mirrored standard activity. Nevertheless, the grouping carried an uncanny vibe. The synchronization appeared deliberately staged, like these timeless nomads had synced their paths for peak theatrical impact. Next, entered the ensemble players. Comet C2005 R2, spotted via the SWAN instrument on the SOHO spacecraft on September 11th, started to gleam enough for unaided viewing close to the Virgo star group. Its streaming tail swept over the dusk heavens, akin to an artist's sweep from the stars, catchable by any observer aware of its spot once nightfall claimed the light. What lay ahead for the comet after its closest solar pass stayed unclear. Plenty of these visitors shatter amid the star's fierce warmth, bequeathing just luminous rubble paths as tributes to their fleeting sunlit journeys. In the meantime, shadowing all coverage in celestial updates was a well-known figure, Apis, formerly labeled 9994D2 APE. This marks the asteroid that formerly dominated concerns in planetary protection. The 400-meter broad crag of material set for a perilously near brush with Earth come April 13, 2029. That pass will position Apophis a mere 32,000 kilometers above our world's crust. Nearer than orbiting weather sentinels, sufficiently close for bare-eyed spotting as it hurtles through the dark vault at 50,000 km/h. Yet the true centerpiece of this stellar spectacle lingered off-stage. Concealed within the announcement of yet another routine, find turned out to be utterly groundbreaking. Dubbed 3I Atlas, or C225N1, it came to light on July 1, 2025, thanks to the Atlas survey team operating in Chile. Unlike the swarm of usual suspects filling up our scopes come September, this one stood apart from the typical rocks and ice balls native to our sun's domain. Far stranger still, it marked the third verified wanderer from beyond our stellar borders, bearing molecular clues destined to upend our understandings of how worlds take shape. At first glance, the Atlas crew picked it out merely as one more hazy speck drifting across the backdrop of stars. Yet deeper scrutiny sharpened its path, and the calculations unveiled a tale of wonder. Bound on a hyperbolic path, this intruder boasted speed aplenty to break free forever from the sun's pull. Originating from distant origins, likely another stellar realm, maybe light-years off, it would graze our cosmic backyard fleetingly before pressing onward into the void's endless night, gone for good. Adding to the intrigue of 3I Atlas was the sheer coincidence of its schedule. Its swing closest to the sun loomed for late October 2025, mere weeks beyond that September rush of space stones. Afterward, much like an actor slipping off stage, it would slip from sight amid the sun's blinding blaze, eclipsed by our star's dominant glow. Still, holding out paid off. By early December, our planet's yearly loop would shift us into prime position, allowing 3I Atlas to peek back out from the solar veil and granting observers their prime shot at probing a genuine fragment of alien cosmic turf. The slot for watching it aligned flawlessly enough to spark whispers of design, perhaps. During its nearest pass that December, the thing would linger at 188 astronomical units distant, about 270 million kilometers off from us, distant enough for no danger at all, yet near sufficient for our top-tier gear to dissect its light in fine detail. One might picture the cosmos handing over a neatly wrapped specimen from foreign skies, right to our observatory's front step, with ideal sightlines and ample hours to poke and prod. So why exactly, then? What explained this abrupt flurry of heavenly happenings bunching up in those tight few weeks? Enhanced scouting efforts no doubt contributed. The Vera C. Rubin Observatory had only just grabbed its debut snapshots back in June 2025, hauling in thousands of fresh asteroid spots within roughly 10 hours of running. Skies now faced more vigilant gazes, tuned sharper than previously, exposing the actual throng of minor players populating our solar setup. Even so, the synchronicity struck as overly neat, too staged to chalk up simply to better spotting luck. Did September 2025 hold some unique pull? A tangle of gravity or yearly cosmic sync that funneled these bits together? Or might this signal the opening scene of a grander stellar saga unfolding across eons we could scarcely grasp? Excitement gripped the stargazers, not dread. Safeguards against world strikers had advanced miles from the era when crashes starred only in blockbuster flicks. Today, we command tools to monitor, profile, and nudge aside any worrisome near-missers. NASA's DART feat lately showed kinetic bashers could indeed tweak a rock's course, as the European Space Eye's Hera probe headed out to inspect the aftermath up close. Yet smarts and readiness hinged entirely on how much lead time they bought us. Such realities stirred uneasy probes into the unseen arrivals, those creeping in sunward, masked in the dazzle right up to their last dash. Had FA-22 aimed to hit rather than harmlessly whoosh past, could we have spotted it soon enough to rally a solid counter? And what did the enigmatic 3I Atlas, bearing its exotic extraterrestrial makeup and cosmic birthplace, reveals insights into the hidden throng of wanderers meandering through the voids among stars? That spike in detections during September stirred a profound shift within the shared realm of scientific awareness. Far from alarm, it marked the dawning realization that our solar neighborhood buzzes with far greater vitality and ties to the vast Milky Way than earlier assumptions allowed. Humanity stood at the threshold of evolving from dwellers confined to one world into engaged players amid galaxy-spanning events. Yet before embracing that shift, clarity was essential on the true nature of the threat had FA-22 collided with Earth rather than gliding harmlessly by. How might such a strike unfold? Delving deeper into FA-22's profile, for Part 2, envision the collision. The equations governing stellar impacts brook no mercy. As asteroid 2025 FA22 hurtled within 835,000 kilometers of Earth on September 18th, it harbored destructive force akin to about 100 megatons of TNT. For context, this dwarfs the Hiroshima blast by roughly 2,000-fold, all packed into one jagged hunk spanning 130 to 290 meters wide. Still, raw power tells just half the tale. The crux lies in its deployment onto Earth's crust. That hinges on an intricate interplay of natural laws, encompassing the trajectory's slant through the air, the body's makeup, and raw chance from the cosmos. Distinguishing a localized disaster from worldwide annihilation frequently boils down to basics like the intruder's build dense metal versus crumbly rubble, its descent steepness or shallowness, or whether it detonates aloft or drills into the soil. With FA22 closing at around 8 kilometers, a pace common to Earth-orbiting rocks, it would squeeze and superheat the air in front, forming a glowing plasma envelope, though not wildly, so as to hint at roots in the distant solar fringes or farther out. Such velocity promised an entry into the atmosphere of breathtaking ferocity. High up, still scores of kilometers from touchdown, the intruder would ignite like an extra star, its forefront surging to thousands of degrees while plowing denser air pockets. For a rock like FA22 in that scale, the probable outcome was a mid-air detonation, shattering fully between 5 and 15 kilometers overhead. Recall the 1908 Tunguska event in Siberia, where a 3 to 15 megaton blast in the sky toppled more than 2,000 kilometers of woodland, leaving no pit behind. FA22's version would eclipse that by a wide margin. Picture yourself 200 kilometers from the epicenter on a bright dawn. The glare hits first, a blaze outshining daylight itself, searing eyes and setting fabrics and foliage, ablaze over vast swaths in hundreds of square kilometers. That heat wave lingers for seconds, sufficient to char bare flesh with third-degree injuries beyond 100 kilometers out. Next arrives the roar. A 100-megaton overhead rupture's blast front would splinter glass over a territory rivaling a modest nation. The pressure surge levels homes within 50 kilometers of the core and inflicts heavy harm to frameworks nearing 150 kilometers away. Sturdy reinforced edifices in the heart zone would buckle badly too. Suppose instead FA22 packed tighter stuff or skimmed in at a gentler tilt, delving further before breaking apart. Ground strike paints a wholly altered portrait of ruin. Drawing from proven simulators such as Impact Earth, a 200-meter iron body slamming at 10 kilometers would gouge out a bowl some 3 kilometers wide and 500 meters down. Right away, the fallout would. Such a collision would spell utter doom for observers in the vicinity. It could instantly obliterate the incoming body, along with a matching volume of surface material, hurling vast quantities of intensely heated fragments along arched paths to shower fiery remnants over expansive areas spanning thousands of square kilometers. The resulting ground tremors would equate to a 6.5 magnitude quake, toppling structures and sparking avalanches throughout a zone stretching hundreds of kilometers. Still, the direst possibility might involve a strike on the sea. Since water blankets more than 70 of the planet's exterior, this stands as the probable fate for any unforeseen space rock. Upon colliding with marine expanses, these interstellar intruders fail to just submerge quietly amid a massive surge. Instead, they unleash a peril far graver, colossal waves. Scientists continue to hone the mechanics behind collision-spawned surges, yet fresh simulations indicate that a 250-meter chunk slamming into profound waters could generate starting swells, surpassing 100 meters right at the point of entry. These surges would spread in all directions at velocities rivaling high-speed jets, retaining sufficient force to menace vast watery realms. A blow comparable to FA22 in the Central Atlantic might unleash 10 meters breakers battering shorelines from Boston to Barcelona mere hours after the event. That said, a key nuance frequently overlooked in catastrophe depictions merits attention. Surge amplitude fades over distance. Traditional fluid dynamics models reveal that such waves shed power during transit, with standard diminutions adhering to reliable formulas. A ruinous 100-meter crest near the strike zone could shrink to 10 nanometers after covering 60 kilometers, then keep waning while traversing oceanic expanses. As ever, the crux lies in shoreline contours and underwater topography specifics. Grasping whether effects stay local or span the globe proves essential to gauging the real peril from urban-destroying space threats. A FA-22 scale event would doubtless wreak havoc on a broad area, endangering millions of lives, yet it scarcely risks worldwide atmospheric shifts or endangering humanity's survival. Such wholesale ruin demands far bigger assailants, those exceeding a kilometer in scale that pummel the world maybe once in several 100,000 years. To put it in perspective, recall the Chelyabinsk incident on February 15, 2013. That 20-minute visitor produced an overhead explosion akin to roughly 500 kilotons of TNT, wounding over 500 individuals mostly via shards from broken panes, and delivering gripping vehicle-mounted videos of celestial junk clashing with contemporary society. The Chelyabinsk fragment measured about 1/10 the width of FA-22, underscoring the rapid escalation of collision force with dimensions. What truly alarmed space safeguard specialists about Chelyabinsk was not its toll, but its total lack of forewarning. The rock neared from the sun's side, concealed amid stellar brightness until seconds prior to air penetration. No ground-based observatory detected its advance. This exposes a core weakness in today's surveillance systems, the solar approach path, where even urban wrecking masses might descend with virtually no alert. FA-22's harmless passage in truth offered priceless hands-on lessons in global space protection teamwork. Its short stint on the European Space Agency's hazard evaluation roster, then its swift delisting once further sightings sharpened the path data, allowed organizations to hone skills in the nuanced craft of alerting folks to risky celestial visitors. How does one alert communities to an imminent danger sans sparking hysteria? How might nations align actions against intruders spanning borders? The International Asteroid Warning Network carried out the incident unfolded as an intense real-world drill amid FA-22's inbound path, evaluating interaction channels and surveillance alignment methods vital for any genuine crisis. Even though it turned out to be merely an erroneous alert in the end, that outcome failed to lessen the worth of the overall MACE ordeal. Quite the opposite, it delivered an even greater benefit, confirmation that the framework held up amid intense strain. Still, the drill exposed key shortcomings persisting in our defenses against celestial threats. Timing stands as the crucial factor in redirecting asteroids. Spotting a risky body sooner means less force needed to shift its course without peril. A subtle push delivered long beforehand avoids frantic interventions at the 11th hour. Today's redirection methods, confirmed effective through NASA's triumphant DART operation, center on forceful collisions. In essence, it's like engaging an interstellar pool with asteroids via fast-moving probes. This approach succeeds, yet demands exact details on the object's makeup, build, and spin dynamics. An asteroid made of loose rubble reacts far unlike a dense metallic behemoth to a strike. Misjudging those factors might spell the line between effective redirection and disastrous breakup. The FA-22 episode acts as a stark caution that Earth resides within a barrage zone of space junk. Much of it consists of innocuous dust specks, no bigger than sand grains, that incinerate safely high in our skies during meteor displays, though now and then a bigger chunk evades our spotting grid. When that happens, the fallout can ravage from urban zones to whole societies. On a brighter note, our vigilance over this stellar district improves steadily. Advanced scanning scopes now activate, boasting unmatched power to spot and follow risky bodies, as orbital heat-sensing platforms prepare to seal the sunward blind spot that let Chelyabinsk sneak in undetected. However, our growing skill at inventorying dangers close to home in the solar setup has also unveiled vast unknowns in the broader universe. Bodies such as 3I Atlas underscore that our star system isn't a secluded outpost, but a brief halt on the Milky Way's thoroughfare, ever welcoming arrivals from the immense voids among the stars. This prompts a compelling puzzle regarding the September uptick. Did it reflect mere chance groupings of separate entities, or might subtler Lynx tie FA-22 fellow near-Earth rocks and the enigmatic star-crossing guest that seized skywatching buzz? To resolve that, we must grasp the additional players on the heavenly platform through those extraordinary fall days. Part 3. Swan, Apophis, and the Comet Surge. As asteroid FA-22 seized attention via its near pass, a different sky actor readied a subtle entry into the dusk heavens. Comet C-2025 R2, spotted by the Solar Wind Anisotropies tool on the SOHO satellite on September 11th, swiftly intensified to unaided eye view while plunging sunward. In contrast to FA-22's reliable charted route, this comet embodied wild instability and caprice. Swan's find of the comet showcased a graceful feature of today's orbital sky science. The device never aimed to chase comets. Its core task centers on charting hydrogen outflows from solar wind clashes near our system's boundary. Yet, as comets near their ultimate sun dive, they emit copious hydrogen-laden steam, catchable from millions of kilometers off. Swan basically chances upon fresh comets via their hydrogen traces, blasting forth amid the vast expanse of space between planets. Come mid-September, the comet C-2025 R2 had intensified its glow to roughly 6th magnitude, teetering on the edge of detectability by unaided eyes beneath clear country night skies. Hobbyists in astronomy started noting appearances positioned by the Virgo star group, adjacent to the luminous star speaker and the ruddy shine from Mars hanging low in the post-dusk western heavens. Its tail extended further and gained clearer form as the sun's warmth prompted the evaporation of unstable frosts off the core, forming the timeless hazy envelope and streaming appendage that have captivated people's wonder across ages. Yet these celestial wanderers prove perilously delicate entities. In contrast to the sturdy composition of stone and iron in asteroids, comets consist mainly of grimy ice clumps, haphazard mixes of frozen water, particles, and carbon-based substances bound loosely by faint gravity and solidified gases. Nearing the sun, the very thermal energy producing their dazzling extensions risks ripping them asunder completely. Numerous comets spotted via Swan fail to endure their initial brush with intense sunlight, breaking up into scattered particle trails that spark short-lived meteor displays prior to vanishing for good. The mechanics of comet awakening feature an intricate balance between evaporation points and radiant warmth from the star. Ice from water starts turning to gas at roughly 200 Kelvin, whereas lighter substances such as carbon dioxide and methane release vapors from positions even farther out from the solar center. During this shift straight from frozen state to gaseous one, bursts of fumes emerge that might sharply shift the path of a comet via forces beyond mere gravity. Such dynamics render the paths of comets challenging to forecast accurately, particularly for those venturing inward for the first time from the remote Oort cloud like C-2025 R2. The odds of C-2025 R2 holding together stayed unclear all through September. New arrivals from the solar system's fringes typically harbor untouched frosts, untouched by notable stellar heat before. Upon facing the sun's rays at last, the swift gas release builds pressures inside that surpass the body's cohesive strength. The central body could fracture into several pieces, with each generating separate hazy heads and extensions, or dissolve outright into a swelling haze of fragments. Still, while this fresh visitor drew focus from backyard skywatchers, a different stellar standout geared up for its turn under the cosmic gaze. Asteroid 993942, Apophis, that 400-meter expanse of rugged stone which formerly led all concerns on planetary protection rosters, presses onward in its relentless path to the nearest asteroid passed by in all documented human annals. Come April 13, 2029, Apophis shall glide by our world at a mere 32,000 kilometers away, nearer than the orbiting relays for global signals, near sufficient to gleam like a swift-shifting point of light, catchable without aid even amid city lights. The pass will happen at about 50,000 kilometers per hour, letting watchers track the rock's shift across fixed stars live, sans any optical gear. The allure of the Apophis event for science lies in our firm knowledge that it carries zero-strike threat for a full 100 years ahead. Scans from radar alongside visual follows have honed its course to unmatched accuracy, ruling out any crash chance in the 2029 skim or for many years beyond. Such assurance lets researchers devote full effort to the extraordinary chance of examining a sizable space boulder in such intimate proximity. The tug from Earth's gravity in that close shave will leave deep and lasting marks. Apophis shall endure stretching pulls potent enough to tweak its spin speed, reshape its outer layers, and possibly unleash slides or shift loose surface grit over its whole form. The space body exiting that brush will show clear signs of transformation. This encounter offers an ideal setting for examining the ways in which near-planetary flybys transform minor celestial bodies across vast timescales. The OSIRIS-APEX endeavor by NASA, essentially a modified iteration of the acclaimed OSIRIS-REx mission focused on sample retrieval, heads toward a meeting with Apophis soon following the 2029 pass. The probe intends to devote several months to charting the asteroid's altered exterior after the event, assessing the modifications to its material characteristics and core makeup induced by Earth's pull. Such insights prove essential for upcoming efforts to redirect asteroids, demanding precise knowledge of how these targets react under applied stresses. Apophis' impending pass, arriving merely 3.5 years following the September 2025 spike, sparks curiosity regarding a potential uptick in near-Earth body occurrences. From a probabilistic viewpoint, such asteroid near misses adhere to no fixed pattern. They amount to sporadic happenings driven by the intricate pulls of gravity that mold the solar system across eons. Nevertheless, the bunching of notable close calls in so brief a span appears to question the idea of complete randomness. Some of this perceived rise arises from detection preferences. Finishing key surveys of asteroids, including Linear NEAT and Space Watch, during the last 20 years has sharply enhanced our capacity to spot and follow risky entities. The Vera C. Rubin Observatory, which obtained its initial light captures in June 2025, marks a further massive advance in observational power. With its vast observational scope and keen sensors, it will repeatedly sweep the reachable heavens every several evenings, delivering unmatched frequency for identifying fresh finds and observing established ones. However, enhanced spotting tools by themselves fail to account for the September rush or the striking variety of participants. In addition to FA-22's tight pass and C-2025 R2's vivid illumination, numerous tinier near-Earth items navigated our immediate stellar surroundings. The body 2025 RJ2 skimmed by at a mere 00. 78 lunar distances on September 15th. Various encounters below lunar range took place across the month, with each duly recorded and monitored via the Global Space Surveillance Network. The timing tied to the season could hint at deeper mechanics at play. As Earth travels its path, it sweeps through varied sectors of the inner solar system annually, and September 2025 may align with traversing a densely occupied patch of orbital clutter. On the other hand, this seeming grouping could stem from elaborate gravitational harmonies capable of aligning several paths over immense temporal spans. Comets introduce further intricacy into this stellar dance. In contrast to asteroids, whose paths remain fairly steady and foreseeable, comets undergo sharp shifts in course from venting pressures and tugs by the massive outer worlds. Extended-period comets originating in the Oort cloud show up with virtually no prior notice, tracing routes untouched by the inner solar system for millennia or eons. Public talks on safeguarding against planetary threats frequently muddle the lines among asteroids, comets, and meteors. Still, grasping these variances holds vital importance for gauging strike dangers and defense approaches. Asteroids function as stony or iron-laden peaks adrift in void, adhering to clear trajectories that evolve gradually. Comets consist of substance-laden forms prone to erratic actions owing to gas releases. Meteors merely represent the glowing trails from tiny fragments incinerating in our air, irrespective of origins from asteroids or comets. Such assortment among minor forms mirrors the tangled past of our solar. The development and progression of planetary systems. Remnants from the initial stages of planet building linger in the asteroid belt situated between Mars and Jupiter, fragments that failed to coalesce into a full world, whereas comets hold onto specimens of the ancient frosts and organic materials originating from the distant edges of the primordial solar nebula. Various groups of these bodies contribute segments to the narrative of planetary creation near stars, and they each introduce unique obstacles for efforts in safeguarding against planetary impacts. During the advancing season of fall in 2025, conditions in the universe aligned for discoveries of exceptional significance. The influx of typical solar system bodies in September stood ready to be eclipsed by an event without precedent, an arrival from a completely separate stellar realm, bearing molecular traces that would question core ideas regarding the assembly of planets and the essence of the space between stars. Yet prior to that, this enigmatic voyager needed to maneuver through the intricate pull of gravity in our solar system's core regions, staying concealed amid the sun's blinding light at its nearest point to the solar position. Upon its eventual appearance in the sights of telescopes during the opening of December, 3i Atlas would reveal itself as wholly distinct from any prior astronomical encounter. Section 4. The Invader from Beyond. On the 1st of July in 2025, a standard computerized scan of the heavens recorded an astonishing find masked as a plain speck of brightness. The Atlas Observatory Network in Riuardo, Chile, had imaged vast numbers of similar items, ranging from asteroids and comets to remote stars moving relative to the fixed star field. However, this specific speck was destined to transform our comprehension of interstellar wanderers. At first, it entered records merely as one more candidate for a near-Earth body, the entity later designated as 3i Atlas, showing no distinction from the multitude of finds archived in the Atlas collection. Software routines marked it for additional scrutiny due to its evident path across the celestial dome. Soon after, observatories globally began charting its course with growing accuracy. Precisely amid this standard process of positional measurement and confirmation, experts discerned an entirely novel phenomenon. The calculations left no doubt. With accumulating measurements sharpening the details of its path around the sun, a single value emerged in sharp relief. Its path's eccentricity surpassed one. Within the principles of sky mechanics, such a marker indicates a hyperbolic path, one endowed with sufficient speed to break free completely from the sun's hold. This entity held no tether to our solar domain. It merely traversed it. 3i Atlas marked solely the third verified interstellar arrival recorded by humanity, succeeding the enigmatic elongated form of 1A Oumuamua, detected in 2017, and the comet 2I Borisov, identified in 2019. Yet, in contrast to its forerunners, 3i Atlas timed its entry ideally for thorough examination. Its route would bring it to its solar nearest point, or perihelion, around October 30, 2025, then to its minimal separation from Earth that same December month at about 1.8 astronomical units. Such a December span equates to roughly 270 million kilometers, a gap vast enough to present no risk whatsoever to our planet, yet near sufficient for in-depth spectral study using our premier instruments. It resembled a deliberate stellar courier, delivering an untouched specimen from a foreign star realm under ideal observational circumstances and with ample prior alert. Still, the path of this body served merely as the initial layer of its enigmas. As measurements gathered over the summer months and into the early fall of 2025, 3i Atlas started to exhibit traits that upended preconceptions concerning the void between stars and the habits of comets. Assessments of its dimensions, drawn from views by the Hubble Space Telescope, placed an upper bound near 5.6 kilometers on the core, although the true extent probably fell well below that figure. This positioned squarely between ordinary comet cores and minor asteroids. 3i Atlas stood out distinctly from earlier visitors from beyond our solar system through its clear display of comet-like traits. In contrast to 1i Oumuamua, which exhibited no detectable coma or tail even amid its baffling non-gravitational push, 3i Atlas gradually unveiled a textbook comet profile while drawing nearer to the sun. Come September, observations from earthbound scopes picked out a prominent coma, a hazy envelope of dust and gas encircling the core, plus early signs of a tail that promised to grow quite striking. Such comet-style outbursts offered initial hints into the body's profoundly foreign makeup. Late in the summer of 2025, as the James Webb Space Telescope directed its infrared analyzers at 3I Atlas, the findings diverged sharply from patterns in homegrown comets. Within the coma, carbon dioxide vastly outnumbered water vapor, registering one of the steepest CO2 to H2O balances recorded for any comet. Grasping the weight of this makeup requires examining comet origins in standard star systems. There, water ice solidifies from the swirling disk of gas and dust at roughly 150 Kelvin, matching orbits some 2 to 3 astronomical units out from a star akin to our Sun. Carbon dioxide, sublimating at cooler thresholds, freezes deeper in, past the frost boundary where chills dip under 78 Kelvin. The overwhelming presence of CO2 in 3I Atlas points to its birth in the icy fringes of its home system, realms far colder and more distant than the birthplaces of most comets here. Perhaps it arose from a disk unusually laden with carbon dioxide, or maybe it coalesced so remotely from its star that water ice barely gathered in meaningful amounts. Yet the oddities in chemistry extended past CO2 alone. Scans via the Very Large Telescope in Chile uncovered yet another enigma: strong nickel signals paired with faint iron traces. Normally, solar system comets carry iron and nickel in balances, mirroring the Sun's own blend, echoing the nebula that birthed them. This evident shortfall of iron, compared to nickel in 3I Atlas, implies some form of chemical refinement or environmental setup alien to our stellar surroundings. With fall advancing and 3I Atlas edging toward its solar closest point, the tail evolved into a multifaceted, eye-catching spectacle. Facilities like the Gemini Observatory, alongside various ground setups, captured diverse tail segments varying in direction and makeup, indicating fresh releases of icy compounds from scattered spots on the core. Under the Sun's warmth, the thing seemed to stir to life after eons adrift in the starless void. Tracking 3I Atlas brought a mix of prospects and hurdles in timing. Nearing perihelion by late October, visibility from our planet would sharpen into frustration from the Sun's nearness overhead. The blinding solar light would cloak it right at the height of its vigor, when heat-driven changes could expose more about its stuff and inner build. Still, endurance paid off. Our world's path around the Sun would steadily enhance sightlines through November, positioning 3I Atlas free of the dazzle by December's start for optimal study. During its nearest pass to Earth in mid-December, though still about 200 times the Moon's remove, it would align perfectly for thorough spectral probes by top observatories. Those weeks out of sight brewed an intriguing puzzle. How would 3I Atlas transform under maximum solar bake? What shifts might unfold? Would the object's peculiar chemical makeup hold firm under such harsh conditions, or might the fierce solar radiation strip away outer layers, exposing altered makeup underneath? Crucially, could this body endure its closest solar pass without breaking apart, or might heat-induced strains shatter it like countless comets that came before? Initial motion-based simulations indicated that 3I Atlas could be remarkably ancient, perhaps exceeding 7 billion years in age, assuming fresh estimates tying it to the galaxy's dense disk stars held true. That age would surpass the lifespan of our whole solar setup, an interstellar drifter roaming void, spaces long before our planet took shape. Trapped within its frozen and stony makeup lay chemical traces offering raw glimpses into primordial galactic states, back when stars birthed at wild paces and heavy metals filled the void far unlike modern times. In contrast to 1IUMU AMU's quick flyby and swift exit, 3I Atlas promised drawn-out scrutiny over several viewing cycles. With its steady inbound speed and handy orbital setup, it stayed observable by top scopes right through 2026, granting a rare chance to probe a genuine fragment from a foreign stellar realm. Yet, as stargazers geared up for prolonged scrutiny sessions, persistent doubts lingered over the body's birthplace and path into our cosmic neighborhood. For how many eons had it roamed the between-star voids? Which stellar home had flung it out? And what forces drove that expulsion? Even more captivating, did its timing align with the September asteroid flurry by mere chance? or might subtler ties link this outsider to the odd bunching of Earth-proximal body brushes? Such seeming harmony in sky happenings started testing belief limits. It began with the stream of near-miss rocks, followed by the flaring icy wanderer, capped by this outsider's debut bearing novel chemical marks. We faced either a wildly improbable mashup of disconnected sky acts or some core force directing this stellar show. While 3 Atlas pressed on toward its solar nadir, veiled by mounting sunlit haze, skywatchers could merely ponder the disclosures due at its December return. Yet, this body already hinted at truths set to overhaul views on world-building, void-based reactions, and humanity's spot amid galactic kin. No more debating if such an outsider would yield fresh cosmic wisdom. The real issue loomed. Were we ready for the fallout from its disclosures on realms past our sun's edge? Still, the true enigma just started to emerge. For as 3I Atlas seized scholarly focus via its exotic reactions and primeval roots, more experts began spotting trends in that September wave, hinting at forces beyond mere stellar happenstance. Part 5. Planetary Defense Wake-Up Call. That September 2025 wave acted as a stark nudge on the shaky state of our cosmic safeguard systems, even after years of tech strides and global teamwork. Though we managed to monitor and profile each major inbound during those tense days, the tight grouping of brushes exposed key weaknesses that might spell disaster should a hazardous intruder slip through at a bad moment. Think on the core issue of spotting angles. Most of our rock-seeking scopes sit earthbound, limited to tracking bodies far enough from the sun's glare in our view. This leaves a huge gap straight toward our closest star. Exactly the inbound path that the 2013 Chelyabinsk meteor slipped past all detection efforts entirely unnoticed. Celestial bodies nearing our planet from the solar direction stay practically concealed right up to the closing moments prior to plunging into the atmosphere. Luckily, FA-22's path steered it far from this observational gap, enabling global observatories to monitor its inbound course over several weeks, leading to perihelion. Had its path tilted otherwise, or if its incoming line had paralleled the Earth-Sun axis more precisely, warnings could have shrunk to just days or mere hours, rather than the ample interval that facilitated thorough profiling and alerts to the public. This solar occlusion forms a critical weakness in today's setup for safeguarding Earth from cosmic hazards. Surveys conducted from terrestrial sites have achieved impressive strides in compiling inventories of objects near our world, yet they face inherent constraints imposed by optical principles and celestial dynamics. No instrument, however advanced, can peer at what's obscured by the sky's most radiant body. The remedy lies in positioning sensing arrays aloft, free from planetary rotation's light-dark rhythm and aerial distortions. NASA's initiative to survey near-Earth objects, set for liftoff in September 2027, will position an infrared observatory crafted to seek out rocky wanderers from a spot lagging behind our globe in its solar circuit. Operating from such a perch, NEO Surveyor can spot incoming masses from angles forever lost to Earthbound watchers. Still, identifying a risky interloper marks merely the initial phase in the intricate sequence of defenses against planetary perils. After spotting one, experts must scrutinize it closely enough to gauge the true danger and select the optimal countermeasure. That demands swift scrutiny from various outposts, exact computation of its path, and in-depth study of its material traits. The Vera C. Rubin Observatory, which recorded its inaugural exposures in June 2025, stands as a transformative leap in pursuing such assessments. With its vast reflecting surface and broad-view imager, it can sweep the observable heavens anew every 3 evenings, delivering unmatched frequency for following fresh finds and observing shifts in their paths. During its debut 10 hours, Rubin identified thousands of previously unknown asteroids, underscoring its power to vastly broaden our tally of bodies prowling near Earth. However, spotting and pursuing these visitors proved futile, absent the means to intervene against looming dangers. Here, NASA's dual asteroid redirection test has furnished essential proof of concept for nudging techniques via collision. The DART probe's collision with the minor body Dorphos on September 26, 2022, shifted its revolution cycle by 32 minutes, surpassing the baseline 4-minute adjustment needed to validate the endeavor. Even more telling, post-strike examinations showed the momentum amplification factor, termed beta, at roughly 3.6, indicating the strike proved almost fourfold more potent than basic impulse transfer would forecast. This boost stems from material blasted outward after contact, functioning akin to thruster plumes to heighten the trajectory shift. Grasping these mechanics proves vital for planning subsequent nudge operations. The European SpaceEye's Hera probe, now en route to the Didymos pair, is slated to reach there in 2026 for a meticulous probe of the DART strike zone. Through Hera's intricate charting and gauging of the resulting depression and scattered remnants, we'll gain authentic benchmarks for collision simulations, aiding in sharpening our insights into how varied asteroid compositions react to such forceful redirects. Kinetic impact represents merely a single option among the arsenal of tools for planetary defense under the TAI framework. When confronting bigger celestial bodies or situations demanding finer adjustments to paths, alternative methods could deliver superior results. Spacecraft known as gravity tractors harness their intrinsic gravitational pull to softly redirect asteroids through incremental velocity shifts built up across years or even decades. Devices employing nuclear standoff explosions might sublimate surface layers, generating intense propulsion akin to a rocket's force. Shepards utilizing ion beams could direct concentrated streams of particles to erode a single face of an asteroid steadily, producing ongoing subtle propulsion spanning prolonged durations. A central lesson emerging from studies in planetary defense underscores that every such method demands considerable advanced preparation to succeed. Delivering a subtle push well ahead, spanning years or decades, avoids the necessity for frantic interventions at the 11th hour. Early identification holds paramount importance for this very reason. The urgency stems not from requirements to relocate urban populations or construct subterranean bunkers, but from the fact that subtle redirection grows vastly simpler as forewarning extends. The International Asteroid Warning Network, formed to orchestrate worldwide reactions to imminent collision hazards, essentially ran a real-time drill amid FA-22's inbound trajectory. FA-22's short-lived entry onto the European Space Agency's hazard evaluation roster, succeeded by its excision following further sightings, offered priceless insights into navigating the fine line separating public alerts from averting widespread alarm. In what manner does one alert the global community to a prospective asteroid peril without sparking financial turmoil or societal upheaval? How might one synchronize multinational countermeasures against bodies capable of impacting various nations? Such inquiries lack straightforward solutions, yet FA-22's close passage furnished a modest risk chance to evaluate messaging guidelines and decision-making procedures. This trial exposed both merits and flaws within our prevailing strategies. Swift global exchange of sighting information enabled hasty polishing of FA-22's projected path, along with immediate delisting from danger evaluations once the peril proved unfounded. Yet, outreach to the public stayed uneven, as certain news sources amplified the preliminary hazard evaluation, whereas others overlooked the event altogether pending verification of the harmless passage. This outreach difficulty partly arises from the built-in ambiguity of initial path calculations. Upon an asteroid's initial spotting, its route suffers from loose boundaries owing to scant sighting records. The zone of ambiguity, encompassing all feasible paths aligning with existing records, might encompass both collision and avoidance possibilities. Solely through extra sightings can this ambiguity shrink sufficiently for firm forecasts. Such dynamics foster a core conflict in planetary defense messaging. Holding back announcements until collision odds reach zero could forfeit crucial readiness windows should the body ultimately prove headed for impact. Conversely, disclosing details amid notable ambiguity hazards, inciting needless hysteria, or, even more perilously, eroding public trust, should evaluations shift with incoming refined data. The escalation in September further exposed lingering shortcomings in our spotting technologies, even amid lately gained progress. Comets with extended orbital cycles, inbound from the solar system's remote zones, may still emerge on short notice, given their sharply oval paths confine most of their journey to far-off locales beyond detection thresholds. Take Comet Swift-Tuttle, which shan't re-enter the inner solar system before 2026. Though its core measures roughly 26 kilometers across, sufficient scale to unleash worldwide catastrophe were its path to cross Earth's orbit. Arguably, the gravest worry involves bodies of city destroyer scale, spanning 100 to 300 meters, substantial enough to wreak havoc on locales, yet compact enough to evade notice until perilously near our planet. Contemporary assessments have documented the majority of objects exceeding 1 kilometer that could trigger worldwide consequences, yet the catalog of tinier asteroids posing potential dangers stays unfinished. Those incidents in September further sparked troubling inquiries regarding our capacity to manage several concurrent dangers. Although FA-22 captured the bulk of media attention, numerous lesser bodies were concurrently navigating the vicinity of our immediate celestial locale. In a situation where various city-destroying asteroids neared at the same time from varied angles, might our systems for detection and analysis become overburdened? Would it be feasible to launch redirection operations targeting numerous objects with today's tools and assets? Such situations are still theoretical, yet they underscore the need for sustained funding and structures dedicated to defending the planet. Finishing the Rubin Observatory survey, launching NEO Surveyor, and advancing redirection methods mark essential advances in building a solidly fortified system for planetary protection. However, these efforts signify merely the initial phase of an enduring, multi-decade campaign to shield human society from strikes originating in space. The encouraging aspect is that defending against planetary threats is essentially a challenge we can resolve. In contrast to seismic shifts, explosive volcanic activity, or additional earthly calamities, collisions with asteroids can be fully averted given ample prior notice and suitable instruments. The principles governing redirection are thoroughly comprehended. The required instruments fall within our present reach, and the structure for global collaboration is already in place. At present, the essential element is the resolve from leaders to sustain financial backing and endorsement for these mechanisms across the extended periods devoid of significant collision risks. Safeguarding the planet resembles acquiring coverage against risks. It appears superfluous until the instant when it becomes vitally essential. That influx in September acted as a pertinent alert that our existence unfolds amid a dynamic stellar setting where such collisions represent not simply a question of whether, but inevitably when. Nevertheless, while experts in the stars labored to record and examine the procession of objects nearing Earth amid those stirring weeks of fall, another form of enigma started to surface amid the gathered observations. The scheduling of these approaches, the grouping of paths, and the striking alignment of an outsider from beyond our system materializing within that tight time frame began to push against the boundaries of mere chance in numbers. Did these signify an exceptionally improbable merging of independent occurrences, or might a deeper force be directing this intricate dance among the stars? Parting 3 Atlas. The mind of humanity is intricately crafted to spot configurations even amid their absence. This inherited trait aided our forebears in spotting dangers concealed in dense foliage and discerning shifts in the calendar that separated abundance from scarcity. Yet, when applied to happenings in the heavens, this very mechanism for identifying patterns might mislead, uncovering links and schemes within the haphazard static of stellar incidents. Still, at times, the configurations hold truth. Reflect on the sequence of happenings. Asteroid 2025, FA-22 glides by our world on September 18th at a separation of two lunar distances. 3 days prior, the diminutive body 2025, RJ-A2, comes within a mere 78 lunar distances. Across that identical period, several more objects close to Earth weave through the space around our cosmic domain, every instance noted and monitored via worldwide observation arrays. Comet C225R2 intensifies in brilliance, nearing the point of unaided visibility after dusk. And in the shadows, the wanderer from interstellar realms, 3I Atlas, nears its closest solar approach in October, following a voyage potentially spanning billions of years. Viewed in isolation, not one of these happenings stands out as unusual. Scores of asteroids traverse within 0.05 astronomical units of our planet each month, adhering to the swift paces orbital mechanics set in motion eons past. Comets customarily wax and glow, and then wane. Interstellar visitors, though uncommon, arise naturally from the processes of planet building and stellar system development elsewhere in the galaxy. Yet, the concentration of such incidents into a brief time frame starts to undermine notions of mere chance in the cosmos. What chance exists for an outsider from beyond our system to show up in the very same period marked by heightened brushes with objects near our planet? How probable is it for a fresh comet find to hit its brightest point right when several space rocks swing perilously close? An intriguing line of thought to pursue concerns gravitational guidance. The notion that 3I Atlas's trek across the Sun's inner realm might alter paths of tinier bodies. Massive entities can tug on the courses of lesser ones via gravity, possibly forming a trail of rubble or a companion swarm that accounts for the bunching of September flybys. Still, the underlying science firmly rejects this idea. 3I Atlas, despite its largest guess diameter of about 6 kilometers, lacks the heft to sway items separated by millions of kilometers. The principle of Newton's inverse square dictates that pulls weaken sharply as separation grows, turning insignificant over the vast gaps seen in those September passes. Furthermore, the path details of the assorted September arrivals reveal nothing linking them to a joint source or mutual motion past. FA-22 traces a standard near-Earth object path featuring moderate ovality and tilt. The diminutive rocks spotted over the course of that month exhibit the complete spectrum of path traits typical of the usual backdrop. Among near-Earth objects, not one displays the escape speed curves, signaling fresh pulls from an interstellar interloper, rendering other ideas more fitting. The seeming bunching stems from spotting prejudices and survey rhythm influences, the Vera C. Rubin Observatory had only begun operations in June 2025, vastly boosting our capacity to spot and follow petite near-Earth objects. Better scanning reach inevitably yields extra finds, fostering a sense of ramped-up bustle despite steady numbers in the actual group. Picture fitting sharp, clear surveillance lenses in a spot once left unwatched. The count of folks passing by stays the same, yet your notice of them surges. In like manner, upgraded sky watches uncover the real abundance of near-Earth objects that lingered hidden from cruder tools all along. The mental quirk known as apophenia, where we spot purposeful designs in scattered data, could likewise shape how we view the September happenings. After initial reports of near misses, experts in the stars and everyday folks grew extra vigilant to later finds. Items that would have slipped by in calmer times grabbed headlines instead, sparking a cycle that boosted the sense of odd goings-on. Nevertheless, even factoring in spotting skews and mind tricks, certain elements of the September spike proved tough to pin on sheer luck alone. Spotting 3I Atlas on July 1st, its course set to shine brightest exactly when near-Earth object buzz hit its height, marks an extraordinary fluke pushing against odds in numbers. Ponder another offbeat possibility. Might 3I Atlas stand not as a lone wanderer, but as the biggest piece in a scattered bunch of star-crossing debris? Should the starting mass have broken apart over its endless voyage across the void, maybe from built-up strains or impacts? When interstellar particles collide with it, the leftover material could disperse over a vast expanse of the cosmos. In such a case, those asteroids spotted in September could be mere pieces from one initial body, each pursuing orbits just varied enough to approach our planet at separate moments. These bits would hold on to their speeds from beyond our system, yet might have been pulled into short-term paths around the Sun by planetary gravity on earlier trips near the core of the solar realm. Still, this idea of breaking apart runs into tough hurdles from what we observe. Examination through spectra of those September rocks reveals ordinary makeup of carbonates or silicates, aligning with stuff born in our own solar neighborhood. Their light bounce patterns, when we have them, fit standard categories for asteroids here, not the odd makeup shown by 3I Atlas. If they all came from the same far-off source, you'd anticipate matching chemical marks throughout the group. Plus, how they move in space doesn't back a shared backstory. Real bits from interstellar space would trace hyperbolic paths like 3I Atlas does, instead of the looped routes tied to objects locked in our sun's grip. The power needed to snag such wanderers into steady orbits close to Earth outstrips what gravity from worlds can provide. Likely, the simplest take turns out truest. What we're seeing amounts to a flurry of rare hits, like bolts from the sky bunching up by sheer luck. The cosmos owes us no even spread of such brushes over our brief spans of time. Chance alone can forge clusters that look purposeful to minds wired for spotting designs. The surge in detection tools during the mid-2020s lets us scan this stellar patch with sharpness and rhythm never before matched. In past eras, skywatchers could have overlooked nearly all those September brushes or caught them as lone happenings scattered through various reports. Now, our skill at finding, following, and profiling several Earth-near rocks at once opens doors to spotting bunches that earlier times never glimpsed. Even so, as logic points to fluke and skewed seeing, that itch of deliberate scheduling lingers. The exact timing of 3I Atlas showing up amid a spike in Earth-close action, alongside its one-of-a-kind chemistry and deep past, hints we might face more than stray overlaps of separate happenings. Clarity could wait until months after its December return from behind the sun's blaze, once we've delved into 3I Atlas thoroughly. In-depth light studies, exact path tracking, and close looks at the September group versus it may uncover links hidden from first glances. But should no ties surface, should 3I Atlas stand truly apart from the September batch, we face a puzzle even more captivating. The cosmos might just hum with more bustle and links than our ground-bound gaze usually grasps. What strikes us as a wild pile-up from our narrow angle could be routine on the grand sweep of the galaxy. It's not about anything tailing 3I Atlas, it's about whether we're at last gaining the eyes to grasp the full tangle of the star-filled world we've long dwelled in. And should that hold, the September wave might mark only the start. This fragment enhances our broader learning on the essence of belonging to a galactic community, one boasting 400 billion stars that perpetually trade substances over immense interstellar voids. Yet prior to tackling those grander inquiries, it's essential to grasp the peculiar conduct of 3I Atlas itself. Indeed, as fall advanced and the extraterrestrial wanderer neared its solar rendezvous, global observatories recorded phenomena and molecular traces defying all precedents from comets, whether native or foreign. Section 7. Odd Actions and Peculiar Traits. While 3I Atlas pressed onward to its October closest solar pass, worldwide instruments started capturing traits that upended core principles of cometary dynamics and alien molecular science. An object first deemed a simple drifter from a distant stellar realm now unveiled intricate facets that defy standard expectations for such bodies' conduct. The standout oddity arose via James Webb Space Telescope data gathered across August and September 2025. JWST's near-infrared analyzers identified a surrounding haze overwhelmingly rich in carbon dioxide, hitting CO2 to water levels topping any prior comet record. Far from merely quirky, this defied orthodox theories on how comets assemble and mature. Grasping the standout nature of this makeup demands examining standard comet origins in stellar setups. Typically, water frost solidifies from nascent planetary clouds at roughly 150 Kelvin, aligning with orbits some 2 to 3 astronomical units out from stars akin to our Sun. Hence, the bulk of our system's comets, birthed in the chilly outskirts past Neptune, retain plentiful water frost blended with assorted fleeting compounds. By contrast, carbon dioxide, subliming at far chillier thresholds, emerges as a key element in cometary builds only beyond 10 astronomical units from the host star, once chills dip under 80 Kelvin. Yet even there, CO2 usually plays a secondary role beside dominant water frost. Such overwhelming carbon dioxide prevalence in 3I Atlas hints at origins in environs alien to our system's norms, or later alterations that winnowed water yet spared CO2. A viable scenario pictures its genesis in the icy fringes of a far vaster or icier planetary array than ours. Should 3I Atlas have coalesced from a formative cloud orbiting a dim star or amid the remote orbits of a multi-gas giant setup, it could hail from a belt where CO2 frost ruled as the chief ephemeral substance. There, water frost might scarcely have gathered, yielding the stark blends JWST spied. On the flip side, prolonged interstellar travel may have reshaped it profoundly. Over eons or epochs, cosmic rays' onslaught might rework outer layers via radiolysis, snapping molecular ties with potent blasts. Should this favor stripping water while safeguarding carbon dioxide, it could account for today's profile, sans invoking bizarre birthplaces. Still, the molecular quirks extended past CO2 supremacy. Scans from Chile's Very Large Telescope uncovered yet another enigma. Bold spectral peaks from nickel particles stood out, paired with oddly faint iron echoes. This veers sharply from our system's norms, where iron and nickel align near solar ratios, mirroring the raw mixes in the birth clouds of their stars. The noticeable scarcity of iron compared to nickel within 3EI Atlas prompts deep inquiries into how it originated, the surroundings it experienced, or the ways it changed over time. A hypothetical explanation points to uneven handling of metal elements amid its voyage through interstellar space, with iron and nickel displaying distinct vaporization points and interaction tendencies chemically. Extended contact with rays from the cosmos or collisions from space grit could preferentially strip away iron, leaving nickel intact in tougher molecular states. Yet, another captivating theory suggests that 3 Atlas originated amid a star system featuring elemental mixes diverging from solar norms. Should the host star have come from another part of the galaxy, say, the dense disk or outer halo zones harboring celestial bodies with odd makeup chemically, then fragments from shattered worlds could inherently show iron-nickel balances distinct from patterns in our nearby stellar region. With the shift from summer into fall as 3 Atlas neared its October closest solar pass, the tail's form grew ever more intricate and strikingly vivid to the eye. Telescopic views from sites such as the Gemini Observatory captured various tail segments varying in direction, hue, and seeming grain dimensions. Such a layered setup hinted at continued release from separate volatile stores in distinct nucleus areas. Underlying the elaborate tail evolution lies the targeted evaporation of diverse frozen compounds. Upon facing stronger sunlight warmth, carbon dioxide starts venting far farther out from the sun than frozen water does, possibly forming an early haze and tail ruled by CO2. Closer in toward the perihelion point, the stirring of water ice could spark a follow-up tail phase, bearing altered light traits and motion patterns. Assessments via polarimetry, which probe how sunlight scatters and polarizes off the comet's haze and tail, offered further insights into the makeup of particles launched from the core. The resulting polarization pattern implied dust specks with atypical spread in sizes or light handling qualities versus standard comets in our system. Such traits might stem from unique building steps in the birth disk of protoplanets or heavy alterations over the extended trek between stars. A notably fascinating feature in 3I Atlas's actions was the evident sporadic surges in glow that arose regardless of how far it stood from the sun. Usually, comets trace steady glow rises heading to perihelion, with luminosity climbing steadily against shrinking sunward gaps. In contrast, 3I Atlas showed recurring bursts, implying deeper inner dynamics at work. Such flares could arise when untouched volatile-laden stuff suddenly faces out as outer shells erode under sun warmth. Numerous comets build up shielding covers of grit and altered carbon compounds that block evaporation until heat strains or vapor forces crack those barriers. Once a breach happens, the fresh frozen layers beneath vaporize swiftly, yielding sharp, short-lived spikes in output. On the other hand, The irregular patterns may mirror shifts deep inside, as 3I Atlas adjusted to sun warmth following perhaps eons in the frigid void between stars. Heat flows seeping through the core might ignite hidden evaporation that splits inner frozen masses, bearing fresh faces to sun rays and sparking chained reaction bursts. Moreover, the spin dynamics of 3I Atlas struck as odd against norms for comets in our solar setup. Light-based tracking aimed at gauging shine shifts during core turns, uncovered either in the extended spin cycle or intricate tumbling dynamics of 3I Atlas, posed significant challenges in establishing its precise rotational interval. Such traits could signal alterations to its framework amid the long haul across interstellar voids, or else mirror the initial rotational vigor stemming from the cataclysm that propelled it away from its originating stellar cluster. Yet, the truly disconcerting facet of 3I Atlas's conduct involved its blend of commonplace features with traits entirely without precedent. Fundamental mechanisms governing the buildup of its dusty envelope, the extension of its luminous trail, and the vaporization of icy components adhered to established scientific norms. Nevertheless, the distinctive molecular markers, progression over time, and physical makeup appeared to contradict long-standing insights from extensive studies of icy wanderers. This mix of routine and otherworldly qualities implied that 3I Atlas embodied a fresh phenomenon in the annals of celestial observation. Far beyond a mere icy body hailing from a distant stellar realm, it offered a glimpse into the mechanics of world building and the conditions around remote suns that diverged sharply from those in our own galactic vicinity. In equal measure, the entity upheld and upended prevailing notions about the development of orbital architectures and the sorts of remnants they dispatch across the cosmos. As 3I Atlas neared its concluding phase prior to closest solar approach and subsequent seclusion amid the sun's blinding radiance, the growing body of sightings sketched an entity resistant to straightforward classification. Its dynamism and light analysis traits firmly marked it as an icy visitor. However, its compositional makeup and operational quirks aligned with none of the recognized categories among denizens of our sun's domain. The core issue hinged on whether these oddities arose from truly bizarre physical and chemical interactions, or merely exemplified the outermost bounds of diversity in cast-off materials from varied planetary setups. Resolution of that puzzle remained deferred until December, when 3I Atlas would re-emerge from solar concealment, granting observatories their prime chance for in-depth scrutiny. Even as skywatchers geared up for an extended campaign of vigilant monitoring, another vein of conjecture started surfacing from the gathered insights. For although 3I Atlas's peculiar traits might trace to rare yet inherent mechanisms, they also provoked disquieting inquiries into the possibility of encountering more than an exceptionally vigorous, icy interloper from afar. Part 8. Alien Tech or Natural Wonder. Amid the era of instant online chatter and rampant fringe hypotheses, it seemed all but certain that 3I Atlas would confront the query shadowing every oddball find in space since humanity first peered beyond our world. Might this signal the handiwork of beings from elsewhere? The entity's singular blend of elements, elaborate patterns of motion, and strikingly opportune arrival for scrutiny had fringe thinkers in overdrive come late September 2025. The buzz kicked off mildly within scholarly forums, where experts highlighted parallels between 3I Atlas and the contentious visitor 1A Oumuamua, which ignited arguments over artificial makeup back in 2017. Each traversed from beyond our solar bounds, each exhibited quirks that strained traditional explanations, each swung by on paths affording prime viewing windows for earthly stargazers. Still, the parallels tapered off quickly, overshadowed by stark and revealing contrasts. In contrast to Oumuamua's puzzling elongated form and baffling push devoid of evident vapor release, 3I Atlas acted precisely as its visible traits suggested. A quintessential icy body, it formed a standard hazy sheath and streaming appendage while drawing nearer to the sun's domain. Its fluctuations in luminosity tracked anticipated rhythms tied to the release of frozen volatiles. Its path displayed the standard bend from solar pull, plus minor deviations straightforwardly attributable. Propelled solely by the release of internal gases, the object showed absolutely no evidence of guided or intentional movement. Chief among these observations, 3IA Atlas displayed zero indications of deliberate propulsion. The trajectory it traced across our solar system adhered exactly to the hyperbolic arc predicted for any free-roaming interloper shaped purely by the sun's gravitational pull. Absent were any adjustments to its route, any mysterious boosts in speed, any signals on radio frequencies, or any hints of engineered forms or constructed features, even when scrutinized through the sharpest lenses of earthly observatories. Science insists on robust proof to back bold assertions, and all data regarding 3I Atlas steadfastly aligned with ordinary cosmic events, though ones far removed from the familiar sights in our stellar vicinity. Each odd mannerism, each peculiar molecular trace, each irregular trait found solid grounding in proven principles of matter and energy. Take, for instance, the overwhelming prevalence of carbon dioxide that rendered 3I Atlas's makeup so striking. Though unseen among comets native to our system, such a blend might straightforwardly arise from origins in the distant fringes of some atypical world cluster. Systems orbiting suns of varying sizes, element abundances, or orbital setups could readily yield icy wanderers bearing exotic blends that baffle those versed solely in the output of our own sun's domain. The seeming scarcity of iron compared to nickel, though baffling at first, might stem from birth amid a star's mix deviating from solar norms or from alterations accrued over eons of wandering between stars. Bombardments by high-energy particles, collisions with space grains, and swings in temperature amid the frigid voids could tweak outer layers in selective fashions, yielding quirky spectral readings free of any need for crafted meddling. The intricate varied tail formations and sporadic flares in luminosity echoed patterns seen in local comets. While pushing the boundaries of documented antics, Comet Hale-Bopp boasted tales of diverse makeups, and Comet Holmes erupted into it with a surge in glow approaching 1,000,000-fold. Everyday cosmic mechanisms plainly held the power to spawn the dazzling and atypical displays witnessed in 3 Atlas. The true puzzle lay not in debating if 3I Atlas bore signs of artifice. Rather, it concerned the persistence of such inquiries. A key factor resided in the deep mental jolt from pondering vast distances between stars. Spotting travelers from alien suns forces us to grapple with the chance of minds thriving across the Milky Way. Our brains, honed by evolution to parse group dynamics and spot intent amid tangled settings, instinctively seek motives or designs in baffling occurrences. This impulse intensifies amid things that defy norms or push beyond standard interpretations. 3I Atlas's odd molecular profile and favorable viewing alignment activated those ancient circuits our forebears employed to spot threats or companions. Confronted by the wholly novel, the mind often leaps to presume some actor or force at work. Yet the cosmos regularly crafts wonders beyond our wildest thoughts. Over 8 billion years it has toyed with forces and substances in extremes from blazing stellar cores to the brink of utter chill in the gaps between stars. Stumbling upon natural happenings or forms that startle us signals no crafted beginnings. It highlights the gaps still yawning in our grasp of the heavens. Coverage of celestial finds in popular outlets often fans the flames of conjecture. Headlines proclaiming scientists' confusion over an enigmatic space wanderer draw far more attention than those describing experts examining a peculiar yet ordinary comet. No matter which version better captures the prevailing scientific view, this dynamic fosters a cycle in which audience fascination fuels exaggerated reporting, which then sparks further conjecture about otherworldly causes. Online platforms intensify the issue by enabling unchecked theories to proliferate more rapidly than rigorous scientific scrutiny. Once experts gather enough details to define an object's traits and dismiss non-natural beginnings, competing ideas have already gone viral and proven tough to debunk with solid facts. The recurring trend throughout history remains unmistakable. From odd pulses to rapid radio bursts, each peculiar celestial find has sparked initial guesses of engineered sources. In all instances, deeper monitoring and examination have uncovered ordinary mechanisms that, though typically more intricate and captivating than first thought, demand no role from alien minds. That said, this pattern doesn't justify halting the hunt for signs of advanced extraterrestrial tech. The cosmos undoubtedly harbors additional smart societies, and certain ones could possess the means for star-to-star journeys or signals. Spotting them, however, demands unmistakable proof of crafted beginnings, patterned radio waves bearing data, items showing deliberate paths defying natural pulls, or formations defying known physical principles. 3I Atlas exhibited zero such traits. Its detected radio outputs were purely ordinary heat glow and gas release lines common in comets. Its path adhered to standard gravity rules, with deviations simply accounted for by ice turning to vapor. Its makeup, as shown through heat simulations and light-based imaging, matched a scattered mix of frozen water and stone, bound by faint pulls and stickiness. Most convincingly, 3I Atlas acted just as we'd anticipate from leftover scraps of world-building near distant suns. Simulations forecast that all star groups hurl out plenty of tiny chunks amid their birth and initial growth. Such remnants drift across the void for eons or epochs until they sometimes cross paths with other solar neighborhoods, appearing as roaming intruders. The makeup and traits of these drifters ought to mirror their home environments. Varying sun sizes, diverse element mixes, unique world setups, distinct heat paths. A genuine piece from a foreign system's cast-offs should appear foreign next to our neighborhood's items, yet follow the universal rules of matter's behavior everywhere. Put simply, 3I Atlas appeared precisely as its nature suggested, a straightforward outcome of world assembly around a remote star, bearing traces of its birth circumstances, unlike those shaping our own sun's brood. Its oddness to earthly eyes wasn't a hint of crafted design, but proof of a Milky Way where world-making setups differ wildly across setups. As 3I Atlas neared its closest solar pass, the growing proof steadily backed everyday reasons for its quirks. Yet that sparked a deeper puzzle than any artificial angle. Where precisely, how many billions of years did this primordial drifter endure from the moment it was hurled from its birth star system until it finally entered our local stellar domain? Answering that demands intricate simulations of cosmic movements and star paths over vast epochs akin to Earth's history. Yet, initial efforts to retrace 3I Atlas's path in reverse across the cosmos and ages are already uncovering intriguing hints regarding its birthplace and the extraordinary voyage that delivered it to our observatories just in time for thorough examination. Part 9: Origins and Biography of 3I Atlas. Reconstructing the life story of a star-hopping intruder involves piecing together a trek potentially outlasting our planet's own span. Within 3I Atlas's composition and orbit lies the preserved imprint of celestial happenings from eons past, when the Milky Way was in its youth, and the arrangement of stars plus heavy metals differed sharply from the current setup. Initial insights into its primordial roots stem from studies of its kinematics. These involve computational efforts to follow its path rearward through the universe in chronology. Early estimates from experts at the European Southern Observatory indicate that 3I Atlas likely sprang from the galactic thick disk, a group of stars born in the Milky Way's initial phases, roughly 7 to 12 billion years back. Should these motion-based projections hold true, 3I Atlas predates our whole solar setup. It has roamed the voids between stars since prior to the Sun coalescing from its ancestral gas cloud, bearing elemental traces from a period of elevated starbirth and galactic metal levels far removed from present norms. Backing for the thick disk idea comes from 3I Atlas's odd makeup. Stars in this old Milky Way layer often displayed distinct ratios of elements versus the fresher thin disk groups, such as our Sun's kin. The noted scarcity of iron alongside unusually high carbon dioxide levels in 3I Atlas could signal its genesis near a thick disk star featuring metallicity, unlike the Sun's and quirky volatile traits. Still, what mechanism allows a minor entity to break free from its home star cluster and embark on an extended interstellar voyage? Such launches usually arise from pulls by massive planets amid the turbulent startup of a planetary setup. As hefty orbs shift closer or farther via tugs from surrounding disk gases, they hurl lesser bodies into escape velocity arcs that eject them forever. Digital recreations imply that each forming planetary realm tosses out enormous amounts of rubble. For each kilogram locked in orbiting worlds, rocks, or icy wanderers, around 10 kilos may get catapulted into the galactic wilds through gravity-assisted boosts. Consequently, the Milky Way ought to teem with countless rogue shards from myriad star-forming zones, an immense scattering of world-building remnants sailing amid the stellar expanse. After launch from its origin cluster, 3I Atlas launched into a lone expedition across the sparse emptiness between suns. Matter's average sparsity out there hovers at about 1 particle per cubic centimeter, surpassing any lab-created void on Earth. Amid such conditions, the wanderer stayed largely shielded from outer forces, locked in an icy stellar slumber mere degrees from utter cold. Nevertheless, its star-spanning path held some drama. Fresh computations by cosmic motion authorities have pinpointed multiple near-misses with alien star groups over 3I Atlas's extended. During its long interstellar trek, in just the last 10 million years, this entity seems to have come within a single parsec, about 3 light-years of no fewer than 6 distinct stars, with every such brush possibly tweaking its path via gentle pulls from gravity. Among these star systems, the standout interaction happened roughly 4 million years back, as 3I Atlas swung to within about 1 light-year of a dim red dwarf located in the Cassiopeia constellation. That near-misses pull was strong enough to noticeably bend the entity's direction, which might account for how its present course fails to trace to any clear origin amid the galaxy's dense disk of stars. Such events spark intriguing inquiries into how the entity's outer layers transformed across its spacefaring odyssey. Bombardment by cosmic rays across eons would slowly reshape the makeup of its bare icy and stony exteriors via radiolysis and nuclear spallation processes. Particles bursting with energy from far-off supernovae, alongside various cosmic happenings, would snap molecular links, yield strange balances of isotopes, and even spawn fresh kinds of compounds absent from ordinary solar system stuff. The deep freeze of open space, hovering near 3 Kelvin on average, likely kept most easily evaporated substances locked in solid states all along the way. Yet, brushes with dusty nebulae in the void or glow from close stellar neighbors could trigger sporadic warm-ups, vaporizing outer coatings and letting them settle anew in altered patterns. Such dynamics might underlie the odd compositions that today's observatories have spotted. Strikingly, 3I Atlas has held its form intact over a billion-year haul, enduring swings in temperature, ray assaults from the cosmos, and hits now and then from specks of space grit. That endurance hints at either exceptional toughness in its build or ongoing self-repair via vaporization and relayering that mends tiny craters from meteoroids and fixes harm from radiation over time. Reaching our solar realm marks the climax of an epic that stretches beyond mortal grasp. Ponder the pinpoint accuracy needed for 3I Atlas to hit the exact moment and angle for prime viewing through human scopes of the 21st century. It endured billions of years amid the brutal void between stars, dodged tugs from scores of star passes, and showed up right when our species had the tools to spot and probe it during that narrow slice of history. The synchrony feels eerily spot on, beyond mere chance. 3. Atlas hit its closest solar point just as cutting-edge orbital eyes launched into service, with our grasp of void-born chemistry keen enough to grasp its import. Had it come a few centuries prior, folks would have shrugged it off as a mere hazy pinpoint in the sky. A bit later, detection might occur, yet full analysis could slip away before it vanished into the starry expanse once more. The saga of 3I Atlas sheds light on the grander tale of how the galaxy unfolds and reworks world-building stuff across the cosmos. All the hefty atoms in its makeup got born in the fiery hearts of long-gone suns, then scattered wide by blasts from supernovae. The carbon, oxygen, silicon, and minor metals forming its frame embody the built-up stellar wizardry from endless cycles of stars that rose and fell long before our own sun took shape. Truly, 3I Atlas acts as a herald from the galaxy's deep past, bearing bits of world-crafting that unfolded in settings worlds apart from what birthed Earth and its neighbors, among heavenly allies. The composition of this entity offers straightforward proof regarding the way unstable substances gather and develop within star-surrounded settings that vary in size, metal content, and movement backgrounds. Yet the deepest element in the life story of 3 Atlas might lie in its disclosure of links among vast cosmic mechanisms. Such a body started out within a disk shaping planets near some other sun, likely from a wholly separate part of the Milky Way. Via an intricate sequence of pulls from gravity, star shifts, and universe mishaps, it reached our viewing instruments at last, transporting details of its beginnings over immense spans of space and eras. Should the idea of its thick disk birthplace hold true, then 3I Atlas would stand as a relic from the Milky Way's early days, an epic of vigorous star birth when the makeup of space between stars differed greatly from current standards. Examining this old drifter might yield understandings of how chemicals in the galaxy changed over time, initial ways planets took shape, and the spread of unstable elements in the galaxy's primeval state. Still, despite advanced simulations and breakdowns of its makeup, key puzzles about 3I Atlas's beginnings linger unsolved. Identifying its birth star or the orbiting setup of its creation proves impossible for sure. The wild pulls of the galaxy's growth have wiped out nearly all signs of its starting path, offering just probabilistic clues to its likely thick disk source. Such doubt highlights the built-in difficulties of digging into space relics. In contrast to Earth-bound remains fixed in layers of rock that can be timed, space rovers like 3 Atlas hold zero straightforward signs of their start time or spot. Rebuilding their tails relies on sidelong hints, makeup of elements, balances of isotopes, path studies, and number-based simulations of galaxy movements. However, these shortcomings fail to lessen the importance of 3 Atlas's role. Lacking precise knowledge of its home ground, we remain sure it bears genuine bits from a foreign realm, shaped in settings unlike our own sun's setup. Each scan through spectra and probe of chemicals adds fresh details on the variety and how planets arise and the array of surroundings where bodies can arise near distant suns. While 3 Atlas pressed on in its last leg to closest solar point in late October 2025, skywatchers readied for the body's short vanishing act amid the sun's blinding light. Those days, right around the solar closest pass, would mark the richest stretch for science in the whole meeting, as peak warmth from the sun would spark the strongest releases of gases and maybe uncover hidden layers kept intact from the body's birth eons back. Yet the very sun blaze that would conceal 3I Atlas in its peak vigor also injected tension into the ongoing tale. Could the body endure the solar closest pass whole, or might heat pressures break it apart into bits akin to countless comets in the past? Upon its return to sight through scopes in December, would it keep showing the odd makeup and intricate action signs that set it apart on its way in? Solutions to such queries had to hold off. Meanwhile, though, the rush in September and 3I Atlas's striking traits were stirring uneasy thoughts on the makeup of our space surroundings and our species' spot inside them. Did this show a chance mix of separate events? Or might hidden links exist, tying the space intruder to the odd bunching of close Earth body meetings? Certain experts started pondering if the occurrences in September went beyond mere random chance, signaling the initial phase of a grander cosmic spectacle unfolding across dimensions that could overshadow our grasp of stellar motions and the development of galaxies. Part 10. Dazzling hypotheticals, celestial chain reactions. When faced with occurrences that surpass routine human encounters, our minds gravitate to dramatic interpretations. Regarding 3I Atlas and the uptick in September, conjectures started to surface concerning potential ripple outcomes. The concept that a wanderer from beyond the stars could initiate a sequence of space happenings capable of reshaping the inner workings of our solar setup. Might 3I Atlas be nudging the belt of asteroids through gravity, akin to a stellar utensil blending elements in a starry broth? Calculations firmly dismiss this poetic fancy. Even with its top projected weight reaching a few trillion kg, 3IA Atlas amounts to a tiny force amid the immense flows of solar system forces. The pull it exerts on Earth-orbiting rocks, separated by millions of kilometers, proves insignificant against the commanding hold of the Sun and major worlds. The principle of Newton regarding inverse squares remains ruthlessly exact in its formulas. Tugs from gravity fade by the distance squared, so 3I Atlas's capacity to sway nearby bodies fades to practically nothing across the span seen in those September brushes. For context, the pull linking 3IA Atlas to the rock FA22, while both lingered inside the Sun's inner domain, equates loosely to the draw between a pair of cars stationed in adjacent urban centers. Still, the ongoing appeal of ideas about gravity guiding persists, highlighting key insights into our mental patterns and bond with vast sky events. We naturally hunt for links of cause amid happenings at the same time, despite the core science rendering those ties unfeasible. Such a habit aided early humans in spotting links of action and result on the ground, yet it misguides us amid sky events spanning realms far beyond personal scales. Wilder ideas of linked chains touch on ties between 3I Atlas and sun outbursts. Might a star-crossing body spark more sun flares or blasts of crown material that could sway weather in space near our planet? Such a thought draws from real worries over sun-Earth ties and how fragile today's tech world stands against magnetic tempests. That said, the rules governing sun behavior involve power levels where brushes with comets hold no sway. Our star pours out roughly 3.8 1026 W of power non-stop, unleashing in a single moment more than all energy used by humanity across its entire past. The pull and field effects from a modest star-hopping comet farther than 100 million kilometers get drowned out by the greater drivers behind sun changes. Sun patterns track established rhythms tied to its core field generator, independent of tiny outsiders in distant zones. Matches between comet showings and sun happenings pop up now and then through sheer luck, though these alignments count as random flukes, not true bonds of cause. The notion of a meteor burst offers yet another alluring yet baseless guess. Might 3I Atlas drag along a trail of rubble that could yield dazzling firework skies as our world crosses the wake? This view seems initially reasonable, since numerous yearly meteor bursts stem from our planet slicing through comet leftovers. Debris trails from comets get abandoned in space. Yet, streams of meteors originating beyond our solar system encounter basic physical barriers, rendering them virtually impossible to spot from our world. Material flung out by 3I Atlas possesses the identical hyperbolic speed of its source body, so whatever bits it releases would likewise flee the Sun's domain instead of forming steady paths that might cross our planet's route. When Earth arrives at the zone 3I Atlas traversed, such release stuff would have spread out over immense spatial expanses, dropping the concentration of particles to insignificant levels. Furthermore, the intense speeds typical of clashes with interstellar bodies ensure that if any stray bits chanced upon our globe, they would slam into the air layer at rates surpassing 70 kilometers far quicker than ordinary meteors from within the solar system. Those extreme speed collisions would generate short, intense bursts of light, not the extended streak seen in standard meteor displays. The notion of breakup illusions marks just one more effort to uncover concealed links tying 3I Atlas to the asteroid brushes of September. Might FA22, along with fellow near-Earth bodies, represent chunks split from the star-roaming intruder amid an earlier swing near the Sun's core, now tracing separate paths that loop them close to us again? Such a picture runs into overwhelming hurdles in terms of path dynamics and makeup chemistry. Genuine pieces from 3I Atlas should hold on to hyperbolic paths and outsider-style compositions akin to their origin. The September rocks show none of that. Their oval trajectories plus standard carbonaceous or silicate builds point to everyday births in the solar system, utterly divorced from anything interstellar. Among the most enduring waves of wild guesses stands the theme of official hush-hush dealings, the notion that state bodies could be hiding signs of wilder impacts or finds tied to 3I Atlas. This notion draws on real worries over openness in monitoring the skies and the risks of secret defense uses for spotting rocks. Still, the facts of today's stargazing routines push hard against tales of broad suppression plots. The World Wide Web of pros and hobbyist skywatchers runs on rules of free info exchange and quick rollout of new finds. Key viewing sites post their watch plans and aim rosters for all to see. Path details for fresh-spotted items hit shared global catalogs mere days after verification. The reward system in scholarly sky science likewise fights against hiding things. Progress in the field hinges on rolling out big breaks in vetted publications and showing work at global gatherings. A plot to bury details on 3I Atlas would demand syncing up thousands of experts over scores of nations, an absurd feat amid the cutthroat drive of discovery. At heart, no solid proof exists for secret influences or buried revelations linked to 3I Atlas. All traits of the thing's motion, makeup, and course align with plain old natural events, though one's pushing the edges of what we've clocked before. That said, while sound reasoning brushes off the flashier wild tales, a single real what if merits deep thought. The chance that we stand at the dawn of spotting way more star-crossers than ever dreamed. The Vera C. Rubin Observatory's game-changing sweep power, paired with advancing orbital heat-seers and tighter global teamwork, might show that items like 3I Atlas pop up far oftener than we thought. Current tallies hint that the Oort nebulous formations and analogous features encircling distant suns are expected to hurl approximately one interstellar wanderer annually into view, observable from our planet with current telescopic surveys. Yet, these projections harbor vast ambiguities, drawn from scant records of merely 3 verified extraterrestrial intruders. Should the actual frequency climb to maybe 10 or 20 such visible interlopers each year, the closing years of the 2020s might herald a seismic shift in grasping the vast interchange of substances on a galactic level. Rather than regarding these cosmic transients as scarce oddities from afar, we could uncover that our own stellar domain is perpetually immersed in remnants originating from myriad alien worlds. Under this outlook, the field of interstellar relic hunting would evolve from a conjectural pursuit reliant on singular peculiar artifacts into a methodical scanning endeavor, adept at delineating the elemental and structural traits of world building throughout the Milky Way. Through examining the trails of ejecta that deliver fragments from remote realms straight to our instruments, we might start charting variations in stellar compositions, stores of fleeting elements, and configurations of orbiting bodies. This kind of insight could mark the deepest alteration in our view of the universe since the Copernican upheaval. No longer would we see our home world and its celestial neighbors as solitary outcomes of nearby star development. Instead, we'd see ourselves embedded in a sprawling galactic network with substances ceaselessly circulating among star clusters over immense spans of space and epochs. From this angle, the uptick in sightings last September could signal not a freakish bunching of disconnected incidents, but our initial peek at the genuine bustle in our stellar vicinity. With advancing sensor technologies and broader monitoring scopes, the present odd spike in detections may turn out to be the norm in a cosmos boasting 400 billion suns, routinely swapping fragments via pulls of gravity and brushes between stars. Still, prior to pondering these grander ramifications, we must endure the pressing trial of 3I Atlas's swing past the sun and its breakout from the blinding solar light. How this entity acts at its nearest solar brush would yield vital insights into the endurance of star-crossing comets and the safeguarding of primordial molecular traces amid intense heat treatment. The risks extended far beyond simple inquisitiveness in knowledge. Should 3I Atlas shatter at perihelion, humanity could forfeit chances to probe unspoiled alien substances for decades or even ages, awaiting the next intruder with optimal viewing angles. Yet, should it hold together, its return in December might deliver humanity's finest ever profile of genuine material from beyond our sun. Part 11, Observational Windows, late 2025 to 2026. The stellar ballet of late 2025, built toward its peak as 3I Atlas, neared its rendezvous with the Sun's fiery core. On October 30th came the projected point of perihelion, that instant when this timeless rover would graze nearest to our central star, following a trek possibly outlasting our planet's own history. However, this pivotal brush would play out beyond mortal sight, shrouded in the blinding radiance of Sol itself. To stargazers across the globe, the perihelion stretch embodied the richest trove of data from the whole event, yet posed the thorniest hurdle for watching. Here, peak solar warmth would spur the fiercest outgassing of volatiles, possibly unveiling buried layers untouched since the Wanderer's birth eons past. Molecules that stayed frozen solid over the endless void voyage would at last vaporize, bearing their spectral fingerprints to whatever scope could peer through the blaze. Detecting the interloper proved challenging, yet the very sunlight that held the key to unveiling the innermost mysteries of 3I Atlas would simultaneously cloak it from terrestrial gaze. Its path brought it to a mere 0.4 astronomical units from the Sun, about 60 million kilometer dipping nearer than Mercury's habitual path. Viewed from our planet, 3I Atlas lingered under 10 from the Sun's blazing face, lost in the hazy luminance that thwarts exacting stellar scrutiny. This imposed break in monitoring sparked an intriguing enigma. Could 3I Atlas endure its solar closest point unscathed, reappearing come December as a unified entity invigorated by newly bared volatiles? Or might the heat's pressures shatter its core, splintering it into scattered pieces forming a widening swarm detectable as distinct cometary forms? The issue of endurance held stakes well past scholarly interest. Remaining whole would imply that wanderers from beyond our system boast enough resilience to retain primordial molecular traces despite fierce stellar warmth. Fragmenting, though visually stunning, could scatter the precious substances, rendering 3I Atlas a prime scientific target, turning an unspoiled relic from a distant stellar realm into scattered, altered remnants. Past examples shed scant light. Most comets in our system that break up near the Sun hail from the Oort cloud's fringes, fresh arrivals facing potent rays for the first time after eons in icy seclusion. 3I Atlas differed sharply, a hardened veteran already proving exceptional durability over its billion-year trek across the void. The stellar twist was striking. Having crossed vast expanses of cosmos and epochs to enter our domain, 3I Atlas would conceal its peak vigor and disclosures behind the very luminary fueling its dramatic shift. It resembled a show where the star vanishes mid-performance during the climax. Still, celestial vigilance yields payoffs. Our world circuit around the Sun slowly refines sightlines for near-solar passers-by. And by December's dawn, 3IA Atlas would start slipping free of the blinding aura into ideal scrutiny zones. Its nearest Earth pass fell in mid-December at roughly 1.8 astronomical units, some 270 million kilometers. Such separation feels immense on human scales, yet it afforded prime setup for in-depth spectral probing, near sufficient for great scopes to gather ample photons, distant enough to sidestep our atmosphere's own heat distortions, and set in the morning's dimness with scant stray light. That December slot promised the finest chance in ages, perhaps generations, to probe untainted extrasolar substance. Unlike 1I or MUA's fleeting incursion and swift exit, 3I Atlas's course and schedule would sustain it in reach of key facilities through 2026, granting extended scrutiny over diverse spectra. In parallel, fellow September sky players geared up for their spotlight turns. Comet C2025 R2 Swan's find, which had steadily gained brilliance through fall, confronted its own endurance trial nearing perihelion in November's start. Newcomers from solar system's edges frequently crack under solar blaze, but should Swan hold firm, it vowed dazzling unaided views for northern skywatchers. The comet's clear-seeing period was tightening as the comet's path propelled it further into the deepening dusk. Yet, veteran seekers of these celestial wanderers indicated that visibility without aid might occur beneath clear, remote country skies. Field glasses uncovered a unique emerald-hued envelope and an extending appendage oriented opposite the solar direction. These marked typical indicators of vigorous outgassing from frozen materials. It stays unclear if such a spectacle persists or concludes in disastrous breakup. Asteroid 942. APUS pressed onward in its relentless advance toward the April 2029 rendezvous, positioning it nearer to our planet than the satellites orbiting at geostationary heights. Even with 3.5 years remaining, terrestrial observatories had commenced their efforts. Comprehensive assessment initiatives aimed to chart the rocky body's exterior traits, spin characteristics, and core makeup prior to the intimate passage that could shift those features. NASA's OSIRIS-APEX probe, en route to rendezvous with Apophis following its planetary brush, performed routine diagnostics, status verifications, and trajectory corrections amid its extended voyage interval. That vessel planned to reach Apophis by June 2029, yielding intimate views of the ways Earth's pull had reshaped the asteroid's material qualities. Yet the boldest boost to our stellar watch systems continued gearing toward full activity. The Vera C. Rubin Observatory's initial exposures showcased remarkable prowess in identifying and following Earth-approaching bodies. Still, the installation lingered in setup stages through fall 2025. When at peak function, Rubin intended to sweep the full observable heavens several times each few evenings, delivering almost instant oversight of stellar movement nearby. Such intensified rhythm promised to transform the spotting and pursuit of asteroids, perhaps showing the September spike as no odd bunching, but a standard glimpse of genuine bustle around our world. Earlier scans, with far wider gaps in their sweeps, could have overlooked numerous targets or overlooked groupings that constant watch would highlight plainly. Our Orbital Detection Array's heavenly segment geared up too for substantial improvements. NASA's Near-Earth Object Surveyor, set for liftoff in September 2027, would unleash a heat-sensing scope tailored precisely for rocky body hunts. Positioned to lag behind Earth along our Sun's path, NEO Surveyor could spot incoming items from the daylight side, hidden from Earthbound scans. Such prowess would seal the spotting void that let the Chelyabinsk impactor strike wholly undetected back in 2013. In action, NEO Surveyor ought to grant early alerts for approaching threats from any angle, wiping out the sun glare weakness that stands as our prime flaw in guarding the globe. For hobbyist stargazers and public researchers, the closing months of 2025 presented various chances to aid active studies substantially. Comet Swan stayed accessible to basic scopes and advanced imaging gear alike, letting keen watchers record shifts in appendage form, luminosity shifts, and likely split occurrences. 3. iAtlas's December return would first benefit southern sky watchers, though its swift skyward dash would soon position it for northern viewers too. Though the comet dimmed beyond naked eye sight absent major optical help, skilled sky photographers might snag shots displaying envelope details and appendage evolution. Crucially, the joint tracking of these varied targets built key know-how in global research teamwork and info exchange. The techniques developed for monitoring the trajectory of 3IA Atlas and analyzing the September surge hold direct relevance for upcoming planetary protection efforts against dangerous asteroids detected on brief notice. Difficulties in observations during the closing months of 2025 underscored the need for backup systems and worldwide collaboration among sky monitoring programs. A lone observatory or detection network falls short in scanning every potential incoming path or variety of celestial body. Full vigilance over nearby space demands joint efforts linking earthbound and orbital instruments operating in diverse spectral bands and observation rhythms. With fall giving way to colder months as 3 Atlas geared up for its concealed brush with the sun, astronomers worldwide rallied assets for an unprecedented effort to study extraterrestrial substances. Implications reached well past scholarly interest alone. Findings from the December viewing period might yield vital knowledge on how planets take shape, the chemical shifts across the galaxy, and how often matter swaps between star systems. Yet prior to that, 3I Atlas needed to weather its close call with Sol. Revelation on its fate stayed out of reach until December, when global scopes would pivot to the early morning heavens to reveal if primordial compounds from a distant stellar realm had withstood a last ordeal on their eons-long path to earthly analysis. Part Dosé, envisioning prospects, possibilities, and hypothetical routes. The blend of advanced spotting tools, better redirection methods, and expanding global partnerships through the late 2020s lays groundwork for varied outcomes in how humans confront space dangers. Events like the September Surge and the 3I Atlas passage offer previews of such paths, from bold command over our stellar surroundings to stark alerts about lingering frailties. In the brightest outlook, setups in tech and organizations from the 2020s evolve into a sturdy framework for defending Earth that wipes out collision threats from rocks while reshaping views of the wider cosmic realm. The Vera C. Rubin Observatory's trailblazing scanning power, paired with orbital heat sensing from NEO Surveyor and akin setups, ensures total grasp of approaching items with warnings spanning decades or ages. Such prolonged foresight shifts redirection from frantic endgame fixes to standard oversight of heavenly paths. Subtle prods delivered long beforehand steer risky bodies onto harmless courses via tested collision tactics honed across numerous DART-class operations. Reliability grows so steady that steering asteroids ranks alongside forecasting quakes and tracing storms as standard means to curb natural calamities. Within this vision, Comet Swan weathers its 2025 sun-grazing swing and delivers dazzling views to the unaided eye across the North's winter skies, sparking fresh waves of backyard stargazers and research fans. 3I Atlas withstands its solar rendezvous unscathed and delivers groundbreaking revelations on chemistry beyond our system and flows of galactic stuff. In-depth study of 3I Atlas cements interstellar relic hunting as a key field of inquiry. Upgraded detection network spots scores more wanderers from afar in the closing 2020s. Every such arrival bears distinct molecular markers, shedding light on varied facets of world-building near foreign suns. By the dawn of the 2030s, methodical review of scattered interstellar remnants furnishes the initial thorough exploration into the chemical makeup of planets amid varied cosmic settings, yields a treasure trove of knowledge. Such breakthroughs propel advances in spectral analysis, exact positional mapping, and synchronized viewing from multiple observatories. These tools shine equally in assessing risky space rocks, allowing early and accurate assessments of their makeup, form, and the needs for steering them away from harm. Global teamwork thrives amid the urgency of common stellar perils. Methods honed for joint scrutiny of the 3I Atlas mature into routine guidelines for managing odd or perilous celestial bodies. Ongoing drills and skill-building sessions sustain preparedness and foster trust in worldwide reaction systems. Interest in stargazing and cosmic studies surges to new heights, with global audiences tracking the steady stream of findings and evaluations. Learning programs seize this momentum to boost understanding of science and logical thinking among varied groups. Merging real stellar dangers with robust tech solutions offers strong proof of the worth in research pursuits and cross-border alliances. Yet other paths bring tougher prospects. The balanced route recognizes that enhanced spotting and rerouting skills will face true trials as the list of risky items grows. Existing scans have pinpointed nearly all rocks over a kilometer that could spell worldwide disaster, though the tally of urban destroyer rocks from 100 to 300 meters stays unfinished. Number-based forecasts indicate that at least one such item will someday near our world, too swiftly for soft redirection options. Such cases demand bolder action methods, possibly involving atomic blasts with hefty engineering and diplomatic hazards. An initial clash like this could feature a find just months or weeks prior to a possible strike, compelling quick choices on rerouting plans amid intense deadlines and widespread attention. Triumph here would affirm spending on world safeguarding and likely spur greater budgets for spotting and rerouting tools. A miss might bring local ruin and deep doubts over our species' capacity to shield against stellar hazards. Cases of halfway wins hold major consequences too. An effort to redirect that averts worldwide doom, yet leaves some strike chance, could spread fragments over inhabited zones, yielding several minor hit spots rather than one vast pit. How the public sees these results might turn from seeing world defense as brave safeguarding to risky tampering with nature's ways. Strikes on water bodies pose especially tricky issues for rerouting plans and outreach to the masses. Most of our planet's face lies under seas, so water hits outnumber land ones for chance-coming rocks. Still, wave creation from sea strikes stays little grasped, with big gaps in today's simulation work. A 200-meter rock hitting deep waters might spark 10-minute surges that threaten whole sea expanses. Shoreline hubs from Boston to Barcelona might suffer ruinous wave assaults hours following a central ocean clash. Alert periods from good spotting could allow escape actions, yet the financial and societal upheaval would loom large, even sans direct deaths. Such cases underscore the need for precise hazard messaging and grounded outreach to the public. Perceptions regarding the efficacy of planetary defense systems, contemporary tools likely possess the capacity to counter the majority of dangers, provided there's ample prior notice. However, situations involving delayed detection or exceptionally massive bodies might surpass the limits of present redirection methods. Although improbable on timescales relevant to humanity, the gravest possibilities pose fundamental risks that existing systems struggle to mitigate adequately. Comets originating from the Oort cloud with extended orbits might reach Earth after just a few months or years of forewarning, bearing sufficient momentum to endanger global society irrespective of redirection endeavors. Bodies of this scale, possibly surpassing 10 kilometers in width, demand redirection forces well outside the scope of what kinetic collision methods can deliver. Employing nuclear blasts for redirection remains a conceptual option, yet the necessary advancements in tech, global collaboration, and setup durations might outpace the limited alert times. Such dire possibilities highlight that planetary defense shields against the bulk of hazards, though not every conceivable one, akin to seismic-proof construction standards or storm monitoring networks. Protective strategies can substantially lessen dangers without eradicating them completely. The aim isn't unattainable flawlessness or an absurd benchmark, but sensible safeguards against plausible perils. Societal mindsets and group behaviors add further layers of difficulty in every circumstance. Responses from the populace to risks posed by asteroids hinge largely on how dangers are conveyed, the nature of press portrayals, and the degree of confidence in expert and official bodies. Reliable data from trustworthy outlets can sustain societal order amid emergencies. Overhyped coverage or unfounded speculations can erode the success of countermeasures, even if the technical means are sufficient. The influx in September offered crucial insights into handling outreach on celestial dangers, yet genuine collision events would carry far greater consequences and sharper focus from the press. The spread of truthful details alongside falsehoods via online platforms could greatly hinder handling of upheavals. Financial ramifications differ sharply depending on the case. Triumph in redirecting a significant peril might spark widespread backing for ongoing funding of planetary defense systems. Unsuccessful or only partly effective actions could lead to more conservative tactics prioritizing relocation and harm reduction instead of direct redirection tries. The expanding role of private space ventures in asteroid operations brings in economic forces that may aid or hinder planetary defense initiatives. Firms driven by gains from asteroid resource harvesting could build assessment and docking skills useful for both mining operations and redirection tasks. Yet, business agendas often diverge from planetary defense imperatives. An asteroid posing a danger while holding prized materials might encounter rival demands from extractive firms and redirection operations. Resolving such disputes would necessitate precise oversight structures to weigh profit motives against collective security demands. Global diplomacy stands as possibly the least foreseeable factor in prospective planetary defense outlooks. Existing partnership structures function smoothly in everyday tasks, but emergencies tied to possible strikes could provoke more rivalrous state actions. Nations may opt for solo redirection projects over unified global efforts, risking clashes or ineffective measures. Paths of technological progress will likewise shape the probability of various outcomes. Breakthrough progress in fields such as fusion energy, propulsion systems, artificial intelligence, or materials, science might vastly enhance our options for deflecting hazards and prolonging the periods we have to respond effectively. On the flip side, a halt in technological development or cuts to budgets for orbital monitoring networks could expose us to dangers that today's forecasts expect us to counter successfully. Issues like climate shifts and various worldwide problems vie for the identical budgets and policy focus required to bolster defenses against celestial impacts. The capacity of officials and the public to concentrate is finite, so risks from asteroids that feel remote or theoretical could slip down the list compared to pressing issues such as wealth gaps, ecological harm, or geopolitical tensions. Nevertheless, the broader view of the universe offered by items like 3 Atlas creates rare chances to bridge earthly divides and emphasize common goals for all people. Realizing that Earth resides in a dynamic cosmic setting full of risks and prospects alike might spark collaboration that earthly dilemmas alone fail to inspire. While we hover on the edge of game-changing advances in tracking and controlling space dangers, the paths we take forward will hinge equally on our societal and governance decisions as on our tech prowess. The wave of events in September, along with the 3 Atlas meeting, deliver both motivation and caution regarding humanity's ongoing ties to the wider universe around us. However, prior to any of these extended outlooks materializing, our initial task is to uncover the secrets 3I Atlas unveils upon its return from seclusion behind the sun this December. The molecular traces and structural traits recorded in that vital viewing period could grant us our premiere close look at genuine substance originating from a foreign solar setup, and it might deliver our inaugural true insight into existing as members of a stellar realm where planets routinely trade their core elements over immense cosmic gaps. Part 13. Conclusion. A cosmic perspective. With cold weather descending over the upper half of the globe, as 3I Atlas gears up for its December comeback from the sun's blinding light, humanity occupies a striking turning point in its bond with the stars. The happenings of September 2025, from FA-22's near pass to Swan's intensifying glow to the finding of our third verified wanderer from beyond, have bestowed upon us far greater worth than mere research findings or confirmations of safeguard measures. They have supplied a fresh viewpoint for contemplating our role amid the vastness. Throughout much of our species' past, the evening heavens looked fixed and reliable. Constellations turned above in timeless designs. Worlds meandered on set routes, while rare comets or meteors offered fleeting hints that the void held some life. Such a view bred feelings of separation from the cosmos. Our world and its dwellers came across as singular outcomes of nearby star formations, cut off from the galaxy's expanse by vast separations and epochs beyond grasp. The September wave demolished that notion of apartness. It revealed our star neighborhood not as a serene edge suburb away from stellar bustle, but as a bustling crossroads where old voyagers from far-off realms frequently traverse, bearing echoes of their birthplaces. 3I Atlas by itself stands as a tangible link to star-making events from eons past in galactic zones our probes might never reach. This goes beyond a mere breakthrough in knowledge. It marks a profound change in how we see the universe, on par with the Copernic revolution or the revelation of an inflating cosmos. We stand not as lone offshoots of one star cluster, but as active players in processes on a cosmic scale have long facilitated the transfer of substances and data across planetary bodies, predating the emergence of Earth itself. The elemental markers embedded in the venerable 3I Atlas convey details regarding rates of stellar nucleosynthesis, circumstances surrounding planetary accretion, and the volatile compositions in settings that predated the ignition of our sun. Every examination through spectroscopy yields immediate insights into the mechanisms that molded the galaxy in its formative era. a time of elevated star birth and markedly altered patterns of heavy element dispersal compared to the present arrangement. Yet the occurrences of September stand out most crucially, revealing our newfound technical prowess to detect, analyze, and possibly engage with this vast interstellar network of substance circulation. The very sensor arrays that followed FA-22's trajectory and will oversee the Apophis 2029 passage hold the capacity to pinpoint and profile extraterrestrial intruders such as 3I Atlas with enough accuracy to glean in-depth scholarly data. We have evolved from mere spectators of celestial events into engaged explorers of interstellar relics. Each advancing survey observatory activated, each refined spectroscopic method perfected, each pact of global collaboration forged, draws us nearer to a full grasp of our stellar surroundings and our place amid them. This shift harbors deep repercussions that reach well past the realms of astronomy and celestial safeguarding. The frameworks needed for surveilling extraterrestrial hazards and probing interstellar travelers' precise tracking apparatuses, swift reaction protocols, and multinational alignment structures offer blueprints for tackling worldwide dilemmas that ignore borders. Efforts against climate shifts, outbreak containment, resource stewardship, and habitat preservation demand comparable blends of empirical insight, innovative tools, and cross-border teamwork. Insights gained from asteroid pursuit and comet profiling might apply just as effectively to gauging atmospheric pollutants, forecasting health crises, or overseeing communal marine and aerial assets. At a deeper level, the expansive viewpoint inspired by encounters with interstellar wanderers like 3I Atlas serves as a remedy against the narrow-mindedness that frequently obstructs joint action on planetary concerns. Acknowledging Earth's position in a vibrant galactic web, where substances perpetually migrate among star clusters over immense spans of space and epochs, renders earthly splits along lines of nationhood, belief, or commerce increasingly trivial. All humanity shares a voyage on this modest orb, navigating a cosmos strewn with primordial remnants from countless distant realms. The carbon within our forms originated in stellar crucibles extinguished prior to the sun's awakening. The hydration we consume might stem from icy bodies originating in the solar system's fringes. The atmosphere sustaining us harbors components that have journeyed star to star for durations exceeding the tenure of intricate terrestrial life. Such awareness recasts habitat safeguarding and communal alliance from vague ethical duties into essential steps toward stellar belonging. We dare not squander the exceptional circumstances permitting elaborate chemical reactions and organic development on world surfaces. Nor dare we splinter our defensive measures via myopic rivalry when confronting threats unfolding across cosmic expanses. The September influx has further underscored the vast gaps in our knowledge of the stellar vicinity and its regulating dynamics. Existing theories suggest that interstellar sojourners ought to appear infrequently, maybe one observable entity every several under ideal viewing scenarios. Such estimates span mere years. Yet should 3I Atlas exemplify standard rather than unusual operational norms, our projections could err by factors of 10 or more. Facilities like the Vera C. Rubin Observatory, alongside emerging survey platforms of the future, stand poised to uncover scores or even hundreds of extraterrestrial wanderers traversing our solar realm each year, the majority eluding present-day instruments due to their diminutive size or faint luminosity. Such revelations would reshape perceptions of matter flows across the galaxy and the pace at which data circulates among distant suns. These findings would likewise provoke deep inquiries into the ubiquity of intricate chemical reactions and perhaps lifelike mechanisms across cosmic expanses. Should the void between stars teem with carbon-based molecules and reactive substances born from varied worldly settings, life's building blocks could prove far more scattered than our present models suggest. Each icy body invading our stellar domain, be it from the nearby Oort cloud or remote cosmic voids, bears traces of the elemental states prevailing at its birth. Acting as innate experimental chambers, they grant unmediated insights into dynamics and settings still inaccessible to even our boldest exploratory probes. Examining these heralds from the stars demands sustained funding for comprehensive detection, pursuit, and analysis tools that enabled the revelations of September. The innovations in collaborative structures enabling recognition of 3I Atlas as a wayfarer from beyond and the secure monitoring of FA-22's trajectory embody generations of research progress and global partnerships. Such assets do not sustain themselves automatically. Instead, they necessitate persistent financial backing, hardware enhancements, and endorsement from authorities and organizations globally. The extended gaps between significant collision risks or dazzling out-of-system arrivals might encourage cuts to expenditures on asteroid safeguards and stellar monitoring networks. That approach would constitute a grave error. The influx of events last September has illuminated how our celestial vicinity buzzes with far greater vitality and linkage than once thought. At last, we are crafting the sighting and interpretive instruments essential for grasping our position amid vast interstellar mechanisms active over eons. Future eras may bring groundbreaking insights into world building, sun life cycles, and the galaxy's molecular progression, drawn from first-hand examination of alien substances routed to our scopes via inherent celestial deliveries. Yet this hinges on upholding and bolstering the very tools behind these breakthroughs. Our options stand starkly evident. We might step forward as dwellers of the cosmos, channeling resources into the systems and bodies required to watch and comprehend our stellar surroundings, all while shielding our world from heavenly perils. Alternatively, we could withdraw into earthbound narrowness, forsaking the broader view precisely when we start perceiving the universe's genuine intricacy and marvel. The September wave and 3I Atlas brush with destiny compellingly advocate the former route. Rare chances have arisen to probe genuine relics from alien solar domains, even as we showcase our advancing prowess in warding off planetary hazards from space. These milestones mark humanity's shift from grounded dwellers to engaged players in immense cosmic events. Still, this evolution thrives only through enduring inquisitiveness, teamwork, and dedication to empirical knowledge that birthed it. The heavens have bestowed extraordinary offerings upon our observational arrays and alert grids. Our fitness to claim these boons rests on decisions forged in the time to come. As 3I Atlas gears up to burst forth once more past the sun's blinding veil, bearing traces of elements from a distant stellar realm and a bygone phase in the Milky Way's growth, humanity positions itself eagerly to absorb the insights it holds on the mechanics of world building and the swapping of celestial stuff insights unattainable through any alternative means. Revelations gleaned from this timeless drifter hold the potential to transform our grasp of planetary genesis orbiting remote suns. The pathways by which vital ingredients for existence scatter across the Milky Way, along with the deeper implications of existing as interstellar dwellers amid a cosmos boasting 400 billion suns perpetually trading their invaluable essences over immense expanses of void between systems, remain key enigmas. That burst in September marked merely the outset. The genuine odyssey of excavating stellar relics and fathoming bonds between stars stretches before us, poised for the insight and unity we must cultivate to decipher the dispatches borne by veteran voyagers such as 3I Atlas through the shadowy voids linking distant orbs.